Okay, so we will, because we need to sort of maximize we have here, and at the same time proportionally maximize the time we're going to be on the hike. Let's just directly jump into, this is Christian's last lecture, right? The third one. Yeah, okay. So without further ado, all right, we will, everything is set up, right? Okay.
Okay. Good change of topic. I'm going to talk about error correction today and ideas for doing practical stuff with logical qubits. So let's jump directly into the thing. So something I got interested in during the last year is the question, if we have now logical qubits, how can we do digital quantum simulation? Specifically, how can we do Hamiltonian simulation? So for quantum simulation, we have two types of approaches. One of them is analog quantum simulation, where you build special purpose quantum systems that mimic certain Hamiltonians. These systems, they usually implement a single Hamiltonian with very high fidelity as well as scalable to large number of particles. And then the second approach, we already learned quite a bit about this in this winter school, is digital quantum simulation, where you have some Hamiltonian which you trotterize, and you sort of simulate this trotterized time evolution on the universal quantum computer. This is, of course, universally programmable, but here you have one global Hamiltonian with very high fidelity, but here you decompose it into single gates, and these gate errors will accumulate with depth. There you can have some savings via error mitigation techniques, but there is not much dispute that these things eventually will need error correction in the future. So what started to interest me is this progress that has been made with Rydberg atom arrays. That you can arrange them in 2D tweezer arrays and move them around arbitrarily. And the breakthrough of the last year, maybe some of you have seen this paper, was that these systems at Harvard have been used to implement actually early fault-tolerant algorithms with small codes. There are a lot of other breakthroughs that I don't cite here, also from Google and so on. But the interesting thing here is that really algorithms with many logical qubits have been produced for the first time. So what I want to ask, can we use these things, these things that do exist now? Can we do Hamiltonian simulation with them? What's actually the challenge? And of course, not the first person to ask this question. For some references, I can of course send you the slides. Many people have of course thought about quantum simulation with logical qubits. And actually something that I recommend you to read is there is a blog about quantum error correction from Arthur Pessa that you can find. You just Google error correction blog, and it basically pops up. And in the first part of the lecture, actually, I will draw quite a lot from this blog. It's actually very, very nice to read. Okay, so the outline of this thing, I will first talk about what's the challenge. Why can we not directly use this logical qubits to do Hamiltonian simulation? Why is it actually difficult? Actually, it could be that I spent most of the time here on this lecture, and play some games with you guys as yesterday to sort of demonstrate you how these logical qubits work. So I will introduce the concept of transversal gates, two-dimensional and three-dimensional codes, how we teleport gates on these codes. I will speak about code switching, and then if there is time, I will move one level higher up the stack and talk a bit how can we then use these things for digital quantum simulation. That's sort of the idea. So let's directly jump in. very high level error correction. I think Harry will give you much more details, about thresholds and code distances and so on. Like an easy way of thinking about this is, how does error correction work? You encode the logical information in the common eigenspace of commuting operators. These commuting operators are called stabilizers. And one of the easiest error corrected codes that you can imagine is this small color code here. Actually, what you have is you encode. You have 7 physical qubits that you use to encode 1 logical qubit. Please ask any questions at any point if anything is unclear. So you have. You have these 3 plaquettes, a red one, a green one, and a blue one. And for each plaquette, you define 2 stabilizers. So you have an operator CCCC and XXXX for each of these 3 plaquettes. You define your logical information in the common eigenspace of these 4 operators. All of them commute with each other. Do you see that? That they commute, right? Because they are overlapping at 2 sides. And XX, so it's very trivial, but it's so important that we write it down once. Of course, all of you know X times C gives minus IY, C times X gives IY. So X and C obviously don't commute, but XX times CC gives minus YY, and CC times XX gives YY, right? So CC and C. So if you have if you have a product of Pauli's, which is an even number, they commute. So all these stabilizers here, these operators, they are called stabilizers. They all commute with each other because they all intersect at 2 sides. So they have a common eigenspace. Commuting operators have a common eigenspace. So what you can actually do is you can write down a Hamiltonian, which is just the negative sum of these 6 stabilizers. And you look at the ground state of this Hamiltonian, you will find that the ground state is twofold degenerate. You have 2 degenerate ground states. One of them looks like this, and the other one is the same state, but every qubit flipped. And this defined as your logical states logical 0 and logical 1. Let me just check if I have a couple of things that I don't forget anything. Right. Okay, so actually you can count how many logical qubits such a code encodes. It's actually the number of physical qubits minus the number of stabilizers. So we have here 7 physical qubits and 6 stabilizers. 7 minus 6 is 1. Why is that the case? The stabilizers are Pauli operators here. And the Pauli operator has eigenvalues +1 or -1. Yeah. So each of these stabilizers cuts the Hilbert space in half. So you have 2 to the 7 basis states, right? So these stabilizers have +1 for half of them and -1 for the other half of them. So each of them cuts the Hilbert space in half, and then you end up with this with these 2 states. Right. So what I want to sort of ask, how can we operate with these logical qubits? We have now this logical information. And so, let me make one more comment about error correction. So the idea about error correction is now you have now your logical states 0 and 1 encoded in this way. And these are eigenstates of all the stabilizers. So every time when you like, you can measure these stabilizers. And since the states are eigenstates of the stabilizers, the state does not collapse when you measure them. So you can measure them and see if an error occurred. These states have +1 eigenvalues for all of these stabilizers. So imagine an error occurred here. We can measure all the stabilizers on these plaquettes. If like a C error occurred here, these two stabilizers will light up. You know, they will show a -1 eigenvalue. So you measure all the stabilizers. If all of them are +1, you're good. You know, but if some of them are -1, if some of them light up, you then, this is called the syndrome of the code, then you can go in and do corrections. Right, so this is the rough high-level idea about error correction. Is this clear? So how can we operate with these qubits? There is an obvious operation that you already see here. Like this operation, 7 times x, you know, this x to the 7, x to the 7th power is apparently a logical x operator, right? Because it flips 0 to 1. So we found one gate already. What is about the logical, if we do c to the 7, is this a logical c operator? It actually is, because if you count the number of ones here, C will give you a -1 for a 0. And all of these states have an odd number of zeros. So applying C to the 7th power will actually do a -1 on all of them. So you get -0, right? So this is also, so these are the logical operators of our code, and they have the correct commutation relations. Like X logical, yeah, you see, so they actually anti-commute with each other because they are product of an odd number of operators. If they would be products of an even number of operators, they would commute. So it's important that we have an odd number of states here. So how can we operate with this code? Actually, so another thing I wanted to say, this is the smallest code that can correct for single qubit errors. Like if an error occurred on a single qubit, like let's say an error occurred on this atom here, number 4, then this blue and this red plaquette would light up. But if an error would have occurred here and here, also these two would light up, so this cannot be distinguished. But actually, if we restrict ourselves that only single qubit errors are happening, you can really correct them. So this code can correct single qubit errors. Okay, so we define our logical operators, X logical and C logical. How can we operate? Can we now do arbitrary single qubit gates with this? Can we rotate this thing on the clock sphere? Like can we do can we do e to the -I theta C logical, for instance, or e to the -I theta X logical? The important thing is, all the operations that you do, they always have to stay in this manifold, 0 logical, 1 logical. This is called the code space. All operations that we do here should stay into the code space. What about these things? Do they stay in the code space? Looks good, right? So can we do this? Do you think this is fine to do on a logical qubit? In principle, yes, right? But let me tell you what the problem is. The problem is, if you do this, you spread errors. So if you look at this operator, it factorizes. It is a product of single qubit operators. This thing here for an arbitrary angle is not. So actually, what such an operation will do, if you would have a single qubit error, it would spread it over the entire code block. This thing we usually call the code block. So it spreads, correctable errors. I told you that this code can correct single qubit errors. It spreads it into actually 7 qubit errors here. Right, so even though this you could in principle do this, it's completely useless because it ruins your error correction properties. You know, it spreads detectable errors into non-detectable errors. And this brings us to the idea of transversal gates. Transversal gates are gates that don't propagate errors within the code block. So this thing is a transversal gate, because applying this gate, single qubit errors will stay single qubit errors. So we are not, for transversal gates, we are not allowed to do anything here that entangles 2 qubits, because this would spread a single qubit error into a 2 qubit error. And in this way, transversal gates, you know, sort of kind of another definition of transversal gates is the logical, for implementing a certain logical gate, you do this exact operation on every physical qubit. Okay. So this is the concept of transversal gates. And we will now discuss what kind of transversal gates do we have in this code. Are there any questions to this point? Was this clear? Honestly, tell me. So we need a couple of gates. Maybe Harry introduced some of them, but we will have a couple of gates here, and we need to get friends with this kind of gates. One gate is the Hadamard gate. Looks like this. It's a single qubit gate. And if you act with a Hadamard gate on an X gate, you get a C. And if you act with a Hadamard gate, like this is like this Hadamard H is also H dagger here. If you act with a Hadamard gate on a C, you get an X. So Hadamard transforms X into C and C into X. Another gate we need is the S gate. The S gate looks like this. This is actually proportional to a 90-degree rotation around the C axis. And what this S gate is doing, the S gate, if you apply it on a C, it stays a C, because you know it commutes with C. If you apply it to an X, here in the dagger, it gets a Y. So S sends X to Y. S dagger actually sends X to minus Y. Another gate that we need is the CNOT gate. The CNOT gate looks like this. The CNOT gate is a 2-qubit gate. So it's a controlled X gate, actually depending on in which state the first qubit is that applies an X operation on the second qubit. And this controlled X gate, what it does is the following. X identity. So if you have an X on the first qubit, it produces an XC. Identity X. If you have an X on the second qubit, it actually stays identity X. And for C, it's actually the other way around. If you have identity C, it becomes XC. And if you have C identity, it stays C identity. So usually what we say is CNOT gate, it spreads X information and C information only in one direction. So X information, you know, it only spreads it to the right, and C information, it only spreads it to the left. I think we don't need the CC gate in this lecture. But these things here, you know, we can sort of collect these gates here that I introduced here. Those are the so-called Clifford gates. And Clifford gates, they are defined. They transform Pauli operators into Pauli operators. So if you apply a Clifford unitary to some Pauli operation, you get a new Pauli value. Right? So you see this all here, you know, it just transforms some Paulis again into Paulis. And this is the reason why circuits composed out of these Clifford gates can be simulated classically. Because all you have to do is, if you want to measure the expectation value of the Pauli at the end of your circuit, you apply just the Clifford circuit to this Pauli, and you just always track how this Pauli spreads out, and there is always one Pauli, because Clifford gates transform a Pauli into the Pauli. That's the simple reason why we can classically simulate Clifford gates. There is two more gates. Now we need, so these can be simulated classically. In order to do quantum computing, to do something interesting, we need non-Clifford gates. And the most important non-Clifford gate is the T gate. The T gate is equal to 1 e to the I pi quarter. And this T gate is actually, it's actually proportional, or it is a Z rotation by 45 degrees. You rotate by 45 degrees around the Z axis. And this is the most important non-Clifford gate. Or yeah, I mean, like if you have a Clifford gate set and you add the T, you're quantum universal.
Yeah.
I mean, I think it's very important that because if you have the T and the Hadamard, you can make any single qubit rotation. Like a combination, if you do, you can try to program this. It's very easy. You can just have these two matrices. If you do HT, you know, you cover the entire block sphere. Right? So it's in this sense, it's pretty important. Right. So let's talk about which kind of gates we can do in this scheme code, which are transversal. And now comes a very important thing, which is super helpful in this context of error correction, which is the following. So we have this state psi that is living in this code space, right? That is spanned by this 0 logical and 1 logical. And the important thing about a logical gate, like if you apply a logical gate to C, it needs to be in this code space. Okay, element of C. This is I call this the code space. Right? So this is what we have to check if we introduce a new logical gate, right? Does it remain in this code space? But sometimes introducing a logical gate, you check, does it stay in the code space, is extremely tedious. You really get old doing this. So another thing that you can do is, like, if you apply one of these stabilizers here to U psi, it just is still U psi, right? So this must still be, the same U psi must still be stabilized by the stabilizers. Now you can multiply this with U dagger from the left. You get U dagger SU on psi is equal to psi. And this means a logical gate, actually, what it has to do, it must transform stabilizers into stabilizers. So this USU dagger must still be an element of this stabilizer group. So this is, every time we introduce a new logical gate, this is the first thing we have to check. does it transform the stabilizers into stabilizers? I would like to make one comment here. These stabilizers, they don't need to be Paulis. Some people do think this, they think a stabilizer is always a Pauli, but it doesn't have to be. It just needs to be an operator that has a +1 eigenvalue on your encoded state. Right. So let's work out some transversal gates in this code. What about the Hadamard gate? Like what we do is we do h to the 7th power. Okay, we apply on each physical qubit, we apply a Hadamard gate. Is this a logical gate? First thing to check, does it transform stabilizers into stabilizers? So h to the 7th power. Let's see what it does, for instance, to the I call this the stabilizers. So we have in this theme code we have 6 stabilizers. I call them X red, X green, and X blue, and C red, C green, and C blue. Okay, these are our 6 stabilizers. So what does h to the 7th power do to these C stabilizers? Anyone tell me? What does Hadamard do to the C operator? Transforms it into X, right? So this simply gets the X on the red, green, or blue, right? So it transforms it. These are again stabilizers, right? And it does the same thing for the X, of course. Right? So our Hadamard gate, if we do Hadamards everywhere, it transforms all the stabilizers into new stabilizers, so it's a valid logical gate. Right? So it stays in the code space. Now let's check if it's really a logical Hadamard. For this, in order to see that it is a logical Hadamard, we have to apply it to the logical operators. So what is h to the 7 doing on X logical? X logical, to remember you, was just X to the 7th power. Here is the X logical operator. What is this thing doing? Yeah, so it goes to C to the 7th, which is our C logical operator. Right? So it's indeed a logical Hadamard. So the Hadamard gate is a transversal gate in this code. We do a Hadamard on each physical qubit, we get a Hadamard on the logical level. And it is transversal because it doesn't spread single qubit errors into 2 qubit errors. Let's check the C naught. So what we do now is we take 2 of these code blocks. So we have now two of these logical qubits. And we do a C naught gate between each pair. Right, we do a C naught here, we do a C naught here, and here, and here. Now between each pair, we do it. These are all C naughts. So what about this? I call this operation here, this red operation, it's doing 7 C naughts, right? So I do C naught to the 7th power. First thing we have to check, does it transform stabilizers to stabilizers? So what is it doing to, let's say we have an X, red, green, or blue, an X stabilizer here on this first qubit, tensor identity on this second logical qubit, C naught to the 7th power. What is this doing? Like C naught, you know, we discussed if X identity goes into XC, right? So actually what it's doing is it's doing X, red, green, blue, you know, tensor C, red, green, blue. You know, for each qubit, you know, like X identity goes into XC. So for an X stabilizer here, we get a C stabilizer here. So it again transforms stabilizers into stabilizers. So it's a valid logical gate, and it's obviously, you know, if you think about our logical operators, it also does the correct thing for the logical operators. So it's a valid logical CMOD, and it's also a transversal gate, because single qubit errors from here will spread to single qubit errors here. But our condition for a transversal gate is that we don't spread errors within the block, right? So it's still transversal, and we can still do our error correction stuff. I'd like to discuss one last gate here in this theme code, which is the S gate. So what happens if we do S to the 7th power? You know, does this transform stabilizers into stabilizers? Let's say we do S to the 7th power. You know, we do on each physical qubit, we do an S gate. So what is it doing to the C plaquettes? You remember what the S gate was? S gate was a 90-degree rotation around the C axis. So what is it doing to the C plaquettes? C. Nothing, right? It stays C. What is it doing to the X plaquettes? Y. Yeah, it gets a Y, a product of Y's on these plaquettes. Is this a stabilizer? Is Y here a stabilizer? Yeah, it's a product of two stabilizers of our code, right? It's X times C, right? It's the so this here is just the X stabilizer times the C stabilizer. Now it's important that we have 4 qubits. You know, because this is actually X to the 4th times C to the 4th, right? And X times C is IY. So you get here an I to the 4th power, Y to the 4th, and I to the 4th is 1. Yeah, so we get it again does stabilizers into transforms stabilizers into stabilizers. It's a valid logical gate. Now we have to check what is it doing on the logical operators on our X to the 7 and C to the 7. Is it really a logical S gate? Let's check this out here. So we have to check like S to the 7th power. So on C logical, it's acting trivial, you know. C just stays C under S. What is S to the 7th power doing to X logical? It goes to Y, you know, like 7 Ys, you know. But now we have to check, is this Y to the 7th power, is it actually a logical Y? This we have to check. So we have 2 operators, we have an X logical and a C logical. And you know, it must fulfill the right algebra. So basically C logical times X logical has to be an I Y logical. So this defines our logical Y operator. Right? Our logical Y operator is really defined as this thing. Logical Y is minus I C logical times X logical. So if you compute what our Y logical is, it's minus I C to the 7th times X to the 7th. And C times X to the 7th is then, it's minus, you get I to the 7th, so you get I to the 8th, I to the 8th and Y to the 7th. But this is actually minus Y to the 7th part. Okay, so our S gate transformed it into Y to the 7th, but our logical Y operator is minus Y to the 7th. So actually, interestingly, if you do an S gate everywhere here, it doesn't do a logical S, it does do a logical S there. Okay, so it transforms Y to minus Y. So it turns out that these are all transversal gates that exist in this 2D code. We have a logical Hadamard, we have a logical C0, we have a logical S gate. So we can do, a Hadamard everywhere, does a logical Hadamard. Actually, this is now where these experiments from Harvard from last year, why this sort of works. In these tweezer arrays, you can move these atoms around. So actually what you can do is you can move these two codes on top of each other, pulse on a laser and do a C0 gate between each pair, and then move these things apart from each other again, and it does a logical C0. But all the gates that we can do here transversally are Clifford gates. So we fundamentally cannot do anything interesting in a 2D code. This is very problematic, and the way how you get we need this T gate somehow here, and the way you get this T gate is via state injection, which I don't will cover in this lecture. I will talk a little bit about some different things. But basically what you do is and you can convince yourself, maybe I have later time to show this to you. What you do is you prepare a state T plus, this is called a magic state. And then here you have your code space psi, and it turns out if you do the following, if you do a C0 gate here, and then measure this guy in the C basis, and then do depending on the measurement outcome. Explain what this means. You prepare this state here, you do a C0 gate, and then you measure here the C basis, and if you measure, you find either a 0 or 1, right? If you measure the C basis. If you find a 0, you are good, you implemented here T on psi. If you find a 1, you have to do an S gate. You have to do a measurement and a feed forward correction. This is what you have to do. And the problem here is this state here, the question is where do we get this magic state from? And this is done by our state distillation. This is a procedure where we prepare a couple of noisy states, and you can apply a circuit to them and then produce better, more purified magic states. I'm not going to explain the details of it. It's just a very complicated procedure. So it's a procedure that requires a lot of resources. But this is a way, this is usually how people imagine fault-tolerant quantum computing in the future, that you have a 2D code, it implements Clifford gates, and then you get the T gate via state distillation. This is how people think about this.
It looks that this state is not deterministic here because the performance measurements will have to.
Yeah, so it's not deterministic. You get randomly a 0 or 1 here. And depending on what you see, you need to do an escape here or not. So if randomly this measurement here, randomly with 50% it implements T, with 50% it implements T dagger. And if you get a T dagger, you need to correct it with an escape to a T. Okay. So actually there is a theorem that if you have a two-dimensional error correcting code, you can only implement Clifford gates transversally. All transversal gates have to be Clifford gates. Let me skip this. But something that is known for a while and that has been experimentally implemented in this experiment from last year, you can go to a three-dimensional code, and these three-dimensional codes, they have transversal non-Clifford gates. And I'm going to explain to you why they have transversal non-Clifford gates. So let's take this code. This is, I think Harry might have introduced this NKD notation in one of his lectures. Just to remind you, this is a 1513 code. It consists out of 15 physical qubits. It implements one logical qubit and has distance 3, meaning that it can sort of correct single qubit errors. So it has 15 physical qubits. It implements one logical qubit. How many stabilizers do we need? So how many stabilizers does this thing have? Who knows? 14, yeah. Did you say 14? So the number of logical qubits is the number of physical qubits minus the number of stabilizers, because each stabilizer cuts the Hilbert space in half. Yeah. So this thing has 14 stabilizers. Where are they? Okay. So turns out that you have an X stabilizers on each cell. Let's take this thing apart. Do I get some applause for animations? So it turns out so you have, this consists of 4 cells, and for each of these 4 cells you have an X stabilizer. So you have an X to the power 8. These are kind of cubes with 8 corners. You have an X to the power 8, an X stabilizer for each of these cells, and the C stabilizers are living here on the surface of the cells. So we have 4 X stabilizers, and I hope that you can see this. If you look inside this tetrahedron, you have 6 facets. Do you see them? There are 3 that separate yellow, green, and blue from the red one. You see there are 3 up there, and down there are 3 again. Like inside the tetrahedron, you have 6 facets. And there are 4 independent facets of the surface of the tetrahedron. 1 for red, green, blue, and yellow. And I mean, you have C stabilizers for each of the facets, but these are the independent ones. All others can be generated by products of the C stabilizers. So we have these 4 X stabilizers. We have 6 inside the cell. 4 plus 6 is 10. And we have 4 independent ones of the surface, gives us 14 stabilizers. And 15 minus 14 is 1. So this encodes 1 logical qubit. Okay. So actually, I forgot something. How much time do I have? Still 20 minutes or so. Sorry, I forgot to mention one thing. This lecture is my most unprepared lecture. You know, I underestimated the effort of preparing lectures. let's before discussing this thing, let's briefly go back to this D code, to this 2D code, and let's see why it does not have the transversal T. Right? Why does it actually not have the transversal T? Let's try. Let's see what the T does. First thing we have to check for a transversal T gate is, does it transform stabilizers into stabilizers? Right, so we do a T on each of these qubits, T to the 7th. Let's apply, like on the C plaquettes, C red, green, blue, T dagger to the 7th. What is it doing? T gate was a 45-degree rotation around the C axis. So what is it doing to the C stabilizers? Nothing, right? Now we have to write down what a T does to an S, what a T does to an X operation. And actually what it's doing is the following. It does e to the minus I pi quarter, okay, S times X. This is how a T gate transforms an X. So if we apply this T to the 7 to the X stabilizers, to X red, green, blue, dagger to the 7. Actually, what we'll get, let's zoom out this X stabilizer here. Okay. So this, we take the X stabilizer here. It transforms it into it goes into SX, right? We get an SX everywhere here, SX, 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 SX. And you get e to the minus I pi quarter to the 4th power, right? This gives us an I. So this I here should already worry you a little bit. So let's see, so we now need to check that this is a stabilizer, right? So something that would be very tedious is, of course, what you can do, and this is also what you find in many papers, is that you could try to apply this thing, this operator, to your code words, you know, to the 0 logical and 1 logical, and check if it stabilizes them. But then you really get gray hair, you know, you really get old doing this. There is a much better way, actually, of checking that this thing is a stabilizer, which is that you verify that it is itself a logical gate that transforms the logical operators as an identity. So what I'm going to do is I call this thing U, a unitary, and we want to see if this is a logical gate by itself that transforms you know, the logical operators as an identity. So C logical should stay C logical, and X logical should stay X logical. So for this, what do we need to do to verify that this thing is a logical gate? Again, we have to check if it transforms stabilizers into stabilizers. So we have to check what is this SX doing to X and C gates. So SX applied to an X, you know, this goes to an identity, and SX, this actually becomes a Y. So this SX here transforms X to a Y. And what is it doing with the C? So this actually, XCX is minus C, and S dagger doesn't change it. So it goes, so X goes to Y, and C goes to minus C. This is what this operator is doing. So what is it doing to let's say to this X stabilizer, right? It transforms it into like the action of this thing, of this I as x, as x, as x, as x. Like it sends this this x stabilizer. It sends it into I times y everywhere. So the problem is actually this I, right? So y would be a stabilizer. It's an x times a c stabilizer, but here we have an I. And even more clearly, you see it if you use this gate to transform, to look at its action on this stabilizer. Then you would have here x, and here you would transform it into a y, right? And this is definitely not a stabilizer. You have a plaquette which is x, y, right? So this T gate on the steam code is not a logical gate.
Where does the y come from?
This y?
No, x, y,
Okay. So what I did is I applied this T gate to this thing, right? And I get this kind of stuff. And now we have to check, is this a stabilizer or not? And the way I did it was to check, you always have to check, does this thing transform stabilizers to stabilizers? And I was looking now, how does this thing transform this plaquette here, right? And if you look, like if you have S X here, like what is it doing to an X here? Here you get Y's, right? So you get X, Y. It's not a stabilizer, yes?
So I don't know this one picture, but where is the I coming from?
The I is coming from, like this is how the T transforms an X. You get this phase factor into the minus I pi quad. Now if you do this 4 times, you get this to the 4th power. So this is the reason why the steam code has no transversal T. Yeah.
Can you also like check like the eigenvalue of this, like I on side for the SX, the eigenvalue?
This one?
Yeah, due to the I, the eigenvalue is no longer plus or minus 1.
It's no longer plus 1. Yeah. So this is problematic. This should bore you with the design. So 3-dimensional codes have transversal T gates, and I show you why. And maybe, you know, if you're clever, you already see why. These are the stabilizers of this code. So let's apply a transversal T to this guy here, to a T gate everywhere. What is it doing to the, so we need to check, does it transform stabilizers into stabilizers? What about this guy? This C facets? Stay the same. What about this guy? X to the 8. It transforms, you know, does this thing here. So you get everywhere on each corner an SX. And now your question, your I, you know, here we had an I because we had e to the I pi quarter. Now we have it to the 8th power, it becomes 1. But this already looks good, right? We are a bit more relieved. Now we have this block, you know, which has SX everywhere. Now we need to verify, is this a stabilizer? You know, if you start applying, applying this thing to the code words of this code and check, does it stabilize it? You die, you know. But the better way is to check if this thing with SX overall here is itself a logical gate. And does it transform stabilizers into stabilizers? So, and some of you might maybe already see it does, right? So if you use this thing, this let me draw this as a cube. So these cells are kind of cubes, right? They don't have the ability to draw their exact shape, but they have 8 corners, right? They are cubes. So on each corner, we have this SX operation on each corner of the 8 corners. And so how does it transform? How does this? I think now of this as a gate, you know, and I want to see how does it transform the stabilizers. So actually, let's say this thing here is the yellow cell, and let's you know apply it to this adjacent blue X stabilizer. What it will do is it will produce here on these 4 edges, it will produce Y's, right? So we get X here times Y here, but this is now a stabilizer of the code. Do you see that? Because this is just, you know, this X stabilizer multiplied with the C stabilizer here. Is this clear, or should I explain it again? So the deeper geometric reason why 3-dimensional codes have transversal T-gates is that that you have these cells, you know, and you have different stabilizers. The X stabilizers are acting on the entire volume of the cells, and the C stabilizers are living on the surfaces. They have different weight. Yeah, this is the deeper reason why you can have a transversal T-gate here. It comes really from geometry. So here we have a transversal T-gate. Now you would think, are we happy now? There is a problem now. So in this theme code, we had a transversal Hadamard. You remember Hadamard transformed X into C and C into X. And the reason why this thing had a transversal Hadamard is that X and C stabilizers were the same. They had equal weight. So it transforms X into C stabilizer and vice versa. Here we have X and C stabilizers that are different. So if you apply a Hadamard here, it would turn this into a C, you know, and it would turn this into an X. These are not stabilizers of the code. So yeah, we are happy we have a transversal non-Clifford gate, but we lose the transversal Hadamard. And we cannot do universal quantum computation. Okay, so this is the deeper reason. So we need to get a Hadamard. Also, somehow we need to get a Hadamard. Actually, there is a theorem, this famous Easton-Mill theorem, that says there is no transversal gate set that you can use to do universal quantum computation. You always need to teleport something in. And if you have these 3-dimensional codes, you can teleport in a Hadamard. Works like this, that turns out that these 3-dimensional codes, you cannot do a Hadamard on them, but very often you can prepare them in a plus state. Sounds a little bit like a contradiction, but you can do this. And then you can, what you do is you do a C0 and a swap, and you measure this thing in the X spaces. And it turns out, you have to believe me, with 50% probability, it implements a Hadamard gate. With 50%, it implements a Hadamard followed by X. So you have to do a correction step, similar as for T-gate teleportation. And this is how you get a universal gate set on 3D codes.
What is the first step you're doing here?
Again, sorry.
What is the first step you're doing? That you already have a plus state. You already have some plus state.
Yeah.
Implemented.
So you cannot, like, if you have this tetrahedron in an arbitrary state psi, turns out that you cannot do a Hadamard.
Yeah.
But what you can do is from scratch, there is a circuit that prepares this thing in a plus state.
Okay.
this is what you can do. So in a way, the way to think about it, you can do a Hadamard, but only at the beginning of the circuit and nowhere in between the circuit. This is one way of thinking about it. And T and Hadamard are universal. Another idea that people discuss is code switching. Saying how many minutes do you still give me? 5 minutes? Okay. Okay, this is good. So actually it turns out if you have this 3D code, you can switch back and forth between the 3D code and the 2D code. And the insight is, if you look at this 3D code, our Steam code that we discussed in such great detail is actually a facet, a circle, you know, an area on the side of this tetrahedron. And the logical operators, this is also something that, you know, the logical operators in such a code, they are not unique. We had the situation here that in this in code, we had C to the 7 is a logical C gate, but we also have a C stabilizer here. So we can always multiply this logical C with a C stabilizer, and then 4 of the C's goes away. And then, you know, just the product of C's down here on this line would also be a logical C operator. They are not unique. Misha actually sometimes likes to say that these logical qubits, they don't really exist. They are sort of, they only exist on a piece of paper, right? So, and actually we can define the logical operators in such a way that the logical operators are actually defined on this surface here. Then you can, you know, you have basically the logical information stored on the surface, and the only thing you need to, like if you want to transform the information now, or if you want to have the qubit really here on the side, the only thing that you need to match is the stabilizers. Actually, the C stabilizers are already good. You know, if you look at one of the sides here, the C stabilizers on these facets, they are the same because C stabilizers were living on the surfaces here, but the X stabilizers are different, right? So we have to force somehow here the X stabilizers. You know that the X stabilizers are living now, you know, on this side, and we force these X stabilizers to have the correct value by simply measuring them. So you measure the X stabilizers here, and then you get a random outcome, either plus or minus 1. And then it turns out that you can make some C operations to correct this. And then you measure the next stabilizer, let's say the red one, you get again, the X stabilizer is randomly plus 1 or minus 1, and you do some C corrections to correct it. And then you measure the blue facet, and then you can, by these measurements of these surfaces, you can separate off this Steam code, and then you end up with a Steam code and something else which you don't care about. And this is the procedure of switching from this code to this code, and then you can switch back. So this would also be a way of getting a universal gate set. I'm running out a little bit of time here, but you know, if you want to have more details, I can explain this to you in a break. Okay, something I wanted to tell you about, which you know, I hope that you appreciate a bit that I took some time, you know, explaining to you code spaces and stabilizers and how you verify that something is a logical gate. But my promise at the beginning of the talk was digital quantum simulation, so I will talk 2 more minutes about this. So the thing that you should get now from this is actually that it's extremely difficult to do arbitrary rotations. Tal, you asked me in the beginning, why is the T gate important? The thing is that with T's and Hadamards, you can produce arbitrary single qubit rotations. And this friend of mine, Cheyenne, who is a postdoc in Misha's group, I asked him once, could you decompose like a square root t gate into Hadamard's and t's, and this is what he came up with. It's extremely complicated, right? But there are methods that have been developed that what you can actually do is, like doing single qubit rotations is extremely difficult, but something that you can do is actually, if you have a situation that you do the same single qubit rotation on each qubit, actually what you can do is you can do only a small number of rotations, build a unitary around it, and then what this unitary is doing is it broadcasts the information of the rotations on the other qubits. Yeah. It turns out that in these operations, E and E dagger, you actually have a lot of transversal gates. So this is something, so, and I stop with this now. So the conclusion of this talk is, you know, for thinking about digital quantum simulations, you have to rethink rethink the thing a little bit. You now have to do things that you would never do if you would do digital quantum simulation with physical qubits, like combining circuits with arithmetic and doing complicated things like that. But in an error-corrected setting, these things actually make sense. I like to say that these things are, in a way, an upside-down world. You know, like things that were very difficult with physical qubits are now easy with logical qubits and vice versa. So what my main interest is here is that you really have to rethink a lot of concepts now if you think about logical qubits. And I'm sorry that I spent so much time on these things, but as I said, we have some breaks and we can discuss all these things in detail. Thank you so much.